Hi, Chris Kuzmal here. We are going to be talking about the derivative of functions. We're going to use an example. This green line is the sine function, and we're going to find its derivative. And we're going to do that numerically. The way that we're going to do that is first we're going to sample the function, just get an idea of what is the value of the function at a given location. I'm going to call that the sample, and that's this vertical line that intersects the function itself, and the location at which it intersects it at is 1.3, and that's right there. Okay, boom. Now then, what do we do with that? We're interested in the how hard we're having to work metaphorically. Climbing up this hill. We're almost where our sample is right now. We're almost to the top of the hill, so we're not working that hard to climb. Let's measure that slope by laying down a stick on the ground and seeing how the stick's angle is. And the way that we do that is, well, how long is the stick going to be? It's going to be defined by this variable called a, and we'll create a second vertical line that is a away. And so we can see that if we vary a, then that varies how far away we put the other end of the stick. And if we put it all the way over here, our stick sort of is sticking through the ground. It's not really giving us an accurate definition of the slope. But let's go ahead and define the 2 points that intersect those vertical lines in our function and the line that goes through those 2 points. And so here we have our bad approximation of the slope, which the slope is slightly up right now, but this other sample point here is so far away that it doesn't accurately represent the slope of the function there. So if we shorten up the distance, then our line tends to flatten out. Now we are near the top of the hill, and so it's a reasonable approximation of the slope here is 0. It's a flat line. But in fact, if we move our approximation even closer, we notice that in fact the actual slope that we intuitively know is slightly uphill is reflected by this line pretty well now that this dx, this a is also, we might be called dx, is pretty small, and so the slope here is pretty small. We would like to have a function that captures this value, a function that is slightly positive at this point, and in fact we can define that by taking f of x plus dx minus f of x and dividing by dx, where dx and a are the same thing. And so this red function is that approximation of the derivative. This is not the actual derivative of the function. This is an approximation where when we calculate this using the definition of calculus, the value of a here is meant to approach 0, and actually in the limit as it actually approaches 0. But here it's not actually 0, here it's 0.05, but it's getting pretty close. Sometimes that's going to be good enough for our purposes. But this is not the actual derivative. The red line is not the actual derivative of the green line. It's only an approximation because the dx is not 0. And the challenge of calculus and the opportunity of calculus and the coolness of calculus comes from coming up with a mathematical tool called a limit, which allows us to treat this value a as not being close to 0, but actually as close to 0 as we want it to be, also known as the limit as this value approaches 0. And that gives us some precision for the definition of the slope of a function at a given point. And that is the derivative of a function.